Assalamu alaikum wa rahmatullahi wa barakatuh. This is the first part of Chapter 4, Mechanical Oscillations. At the end of this chapter, we're going to be able to define the oscillatory motion, indicate the types of oscillations, specify the characteristics of an undamped oscillatory motion, establish the differential equation which governs the simple harmonic motion of a horizontal elastic pendulum, analyze the graphs of the energy of the free undamped oscillations of a horizontal elastic pendulum, finally define the driven oscillation. Mainly in this part, we're going to talk about the first three objectives. Before starting with the lesson, it's better to remember a little about derivatives. In this lesson, we're going to talk about sine functions. The derivative of sine of u of t, where u is a function of t, is u prime of t times cosine u of t. And the derivative of cosine u of t is minus u prime of t sine u of t. For an example, if I have x equals to a sine omega 0 t plus phi, then omega 0 t plus phi represents a u function of t. And the derivative of u of t is just w0. So x prime is omega 0 times a cosine omega 0 t plus phi. In the previous years, we used to study three types of motions: rectilinear motion, rotational motion, curvilinear motion, and we used to study their time equations for position and velocity. Have you heard of other types of motion? Let's think together. A swing pushed then left on its own moves to and fro. A tuning fork also, when stuck and left on its own, vibrates, both with a constant frequency. And also remember a vertical spring studied before when it was at equilibrium in grade 9. If we displace the mass and leave it, it will oscillate. All these and other represent periodic motions of some characteristics. What is periodic motion? It is a motion that repeats itself identically during a constant interval of time called period. These motions are oscillatory. But the question is, are all periodic motions oscillatory motions? Check these motions and then I will repeat the question. The Ferris wheel, clock, earth, all these are periodic. Can we consider them oscillatory? No. Then, not all periodic motions are oscillatory motions, yet the opposite is correct. What are oscillatory motions? Oscillatory motion is a to and fro motion of an object between two extreme positions around equilibrium position. To indicate an oscillation, a particle started from one extreme position should go to the front, reaching an extreme, passing through equilibrium position, then it goes backward to the same initial extreme position, also passing through the equilibrium position. The particle will follow its way 2 times. Consider the vertical pendulum starting from the equilibrium position. It moves upward, stops at the maximum position, then turns backward to pass again through the equilibrium position, reaching the other extreme, finally backward to the equilibrium position. Again, it follows each path twice. What about starting from any point through its motion? It will come back again towards its initial position. Mechanical oscillations or oscillatory motions can be classified into 3 types of oscillations. Forced oscillation, which is reduced in the steer, driven oscillations, and free oscillations, which also about damped free oscillations or undamped free oscillations. I would like to ask you a question, and mainly who have tried riding an old car and a modern car will answer. Why does the modern car do no disturbance on a poorly maintained road with several bumps, unlike the old car? To answer the question, you should first know that cars contain oscillatory systems. Then, you should follow us with the lesson. Finally, you will find the answer, but keep it in your mind and don't forget it. What are free oscillations? An oscillator is said to be free when it is not subjected to any external energy input after it has been set in motion. And this motion is characterized by, first, period, which is the duration of a complete oscillation. It is taken between two maxima. It is the time taken by one cycle, as it's shown in the figure. It is expressed in seconds. Then we have a frequency, which is the number of oscillations performed per unit of time, and it's expressed with F equals to 1/T. Its unit is hertz when the time is taken in seconds. Finally, the amplitude, which is the maximum deviation of an oscillator from its equilibrium position. But we should distinguish between the amplitude and elongation. The algebraic measure of a deviation, any deviation from the equilibrium position, is called elongation, y or even x. But the maximum deviation from the equilibrium position, and always positive in value, is called the amplitude, A, which is expressed in meters. In undamped free mechanical oscillations, the oscillator oscillates with a constant amplitude, and it oscillates with a constant period called natural period T0. The natural period is the smallest possible period of oscillations. Note that in this video, we are considering the undamped mechanical oscillations where the amplitude is constant. In this case, mechanical energy is conserved because there is no friction, no non-conservative forces. But it is good to know how could the damped oscillation be. Damped oscillations, because of the existence of non-conservative forces, mechanical energy is not conserved, the amplitude decreases over time. It's time to make application. A horizontal elastic pendulum consists of a solid S and a spring R. S can move without friction on a horizontal rail, and its center of inertia, G, moves along the horizontal X prime, OX. X is taken as the gravitational potential energy reference level. An appropriate device makes it possible to record the abscissa X of G as a function of time. Find the characteristics of this pendulum, period, frequency, and amplitude. Starting with the period, which is the total duration over the number of oscillations. Let's take 4 oscillations because it is indicated in the graph. Then divide the time taken by 4 oscillations, which is 4.04 by 4, and the answer is 1.01 seconds. Frequency, which is the reciprocal of the period, 1/T, 1/1.01, the answer is 0.99 hertz. Finally, the amplitude, which is the maximum, and is taken 2.5 centimeters, which is 0.025 meters. What are the main ideas in this part? Mechanical oscillations can be free, maintained, or forced. Free mechanical oscillations can be damped or undamped. An oscillation is characterized by its period, frequency, and its amplitude. This is the end of the first part. Study well, and thanks for watching.